As Capcom games rolled into arcades in 1984, Nintendo's Famicom was experiencing a boom after launching the previous year. This led to Capcom contracting developer Micronix to port several of its arcade games to the system. Following Micronix's port of Ghosts and Goblins in the summer of 1986, Capcom took Famicom development into their own hands and released Commando in September of that same year. While Micronix games ran at a reduced frame rate, Capcom's Commando port ran at 60 FPS, albeit with an army of asterisks. Screens may output garbage graphics. Scrolling flies off the rails, and sprites will sometimes clock out for lunch. If programming informed Capcom that the game was working but was also flying apart, Capcom's response was, "Fly her apart then." So the fun factor is there, but so is the jank. That said, it looks like Commando was perhaps in mid-optimization at the time it was shipped. Let's talk software development for a moment. Many of you can relate to this. Ideally, programming has an appropriate amount of time to start, enhance, tweak, test, debug, fix, optimize, and finish software. Realistically, that timeline is start and finish. Because hard deadlines exist, development is get it working first, and then optimize it if you have the time. I think Capcom got Commando working, started to optimize it, and then shipped it. Check this out. As time moves forward, new frames are output to the television. 2 consecutive frames, numbered 1 then 2, are seen here. The period between frames, referred to as vertical blank or V-blank, is used to perform graphical updates. Since we aren't drawing to the screen, it makes sense to use this period to mess with graphical changes. Commando has 2 subroutines for pushing palette information to the PPU while between frames. The first subroutine bank switches to the appropriate bank for palette retrieval, loads each color from that ROM bank, and saves it to RAM. The second subroutine loads the same colors from the same place in ROM, saves them to the same place in RAM, and also sends them to the PPU. Both the first and the second are called between frames. Neither of these 2 subroutines will work by itself to get palette information to the PPU. They need each other. The first is required because it selects the proper ROM bank for a palette transfer. The second is required because it performs the palette transfer to the PPU. The RAM they both reference would seem to be irrelevant. Why were palette updates split into 2 subroutines? Why did both subs write to RAM but neither read from it? This could just be leftover code, or an optimization was in progress, and here's why I say this. Graphical updates are sent during the vertical blanking period, the time between frames. Commando sometimes takes too long to send its graphical updates during this period. It tries to do too much. This results in artifacts like a jump in scrolling. Since time is short during VBlank, logic for graphical updates should be minimized. If more time is required, one may consider spacing out graphical updates across the VBlank times between multiple frames. This palette example might be evidence of optimization. Place color lookup logic and queuing in one subroutine to execute sometime before VBlank, and then send that queued data to the PPU via a second subroutine during VBlank. They didn't quite get there, of course. The logic split amongst the subs is wrong, and the first sub still executes inside VBlank time. So how does Commando handle graphical updates? Why does it glitch? And how do we fix it? What are the graphical needs for an NES game? Color palettes for backgrounds and sprites. Tile patterns for backgrounds and sprites. A tile set for defining 2 screens worth of backgrounds. The colors for said backgrounds, and of course, sprites, all need to be defined. The background tile set and the colors for that tile set are stored in VRAM. That's your 2K of VRAM inside the NES. The sprites are stored in OAM, which is inside the NES PPU. The palettes are also stored inside the PPU. That leaves the pattern tables for backgrounds and sprites. These are provided by the cartridge. They might be stored in 8K of character ROM like in Super Mario Bros. They might be provided by an 8K window from a larger bank-switched ROM like with Mega Man 3. Or they might be copied out of program ROM and placed into 8K of character RAM as needed. This is what Commando does, and its procedure for loading on the fly adds to the pileup of graphical update logic for all of these things we see here. So how does Commando handle all of this? The game scrolls vertically, so the two name tables for backgrounds are stacked on top of one another. When you press Start, playfield graphics are loaded into the lower half of the second pattern table. Those graphics are used to build the lower name table, our first background. This is the area where the player is dropped off by a helicopter. The upper name table still contains the title screen. It looks wrong because the patterns for the tiles have changed. An exception here are the block letters for Commando. It is interesting that Capcom only populated one name table at the start. They could have loaded a full second background's worth of tiles in the top as well, or even half a background. Consider that Super Mario Bros. Loads a half screen's worth of extra tiles to the right of the scroll window and maintains that half screen buffer as Mario moves to the right. Commando does not do this, and instead updates the topmost two rows of tiles as they scroll into view. This process repeats continuously as the game scrolls, and this adds to our graphical needs during VBlank. Well, that takes care of name table updates. How does it update the attribute table that holds the colors for these backgrounds? Whenever the scroll window reaches a name table boundary and scrolls into a new background tile set, Commando shoves all of the attribute bytes for a full background into the attribute table for our destination. That is 64 bytes pushed during a single vertical blank, plus any other graphics data it wants to push. In fact, Commando not only needs a lot of time during VBlank, it needs multiple VBlank periods for graphical updates during scrolling. Let's illustrate our distribution of that graphics logic. It is time for specifics. Here we have two VBlank periods that occur across 3 frames. Most of the graphics for frames 1, 2, and 3 have been removed here because we are interested in these two VBlank periods between those frames. When you walk upward and it is time for the window to scroll across a name table boundary, we hit VBlank A for our first set of graphical updates for scrolling, and here is what happens. The game turns off rendering and sends a full background palette update, a 64-byte full screens attribute table update, the first new row of 32 tiles, and all of the sprite information to the PPU. We obviously rolled into frame 2's draw time. The logic then sets the desired scroll window position at this moment in time here on scanline 10, and rendering is turned back on here on scanline 11. It's a little too late to reposition the scroll window. Now the VRAM address can jump around as needed when graphical updates are sent during VBlank. When those updates are done, the scroll position is reset before the end of VBlank to make sure we get the PPU address back to where we want it to be before we start drawing again. Well, we missed before the end of VBlank by about 11 scan lines. So what happens? The PPU has had sprites and background rendering disabled until this point in time, so it just outputs the brown backdrop color before this. Rendering is re-enabled here, and the scroll window has a Y position kinda left over from when we added our new row of tiles, a row that starts higher from where we used to be. The PPU just picks up drawing to the screen, and we're in the wrong location. Graphics have been pushed down way too much. The volume of graphical updates performed during the first VBlank after crossing into a new name table at any point during gameplay above ground makes this jump in scrolling inevitable. And there is still more work to be done during the next vertical blanking period, VBlank B. We set a flag during VBlank A to, hey, write a second row of tiles, and it is picked up here during VBlank B. The second row of tiles is written to the name table just like the first. It takes maybe half of vertical blanking time to do this. Next, it does something it should not. By programming's design, Commando uses a set of virtual macro blocks to handle collision detection for the environment. A background is divided into an area of 16 blocks by 15 blocks. Each block has 1 byte that defines obstacles inside a 2x2 tile area. All 240 of these blocks are maintained in RAM. As you move around the screen, the obstacle bytes are used to check for collision. They're updated as you scroll upward. Each time the second of 2 new rows is updated, Logic also writes a new row of 16 obstacle macro blocks to RAM. My problem here is that these bytes have nothing to do with graphics. Do this work outside of VBlank. Don't waste time inside of it. The loop takes about this long. After this, sprites are written to OAM as usual. This process completes just before the new frame is drawn. Technically, it was still a little late, but no graphical glitches occurred. So frame 3 snaps the scroll window back to where it should be. All is well, except the tiles look wrong until they fix themselves. This doesn't really make sense, does it? We just wrote new background tiles for 2 rows over the last couple of frames. Everything should be in place. And it is. But programming made an interesting choice when it comes to the pattern tables and Commando. And that interesting choice was that for each time we cross a name table seam in Commando, we also have to shove over 2,000 bytes of data to the pattern table. I'm not joking. There are 2 pattern tables. Let's call them first and second, like so. For sprites, Commando uses the first pattern table. For backgrounds, it uses the second. At the start of gameplay on the first screen, we see several trees. There's a single tree at the bottom left and a group of 3 trees at the bottom center area. Separate tile patterns aren't required for each tree. Any tiles in the second pattern table can be used as many times as necessary to build the background. But what Commando does is use the top half of the second pattern table exclusively for the top name table and the bottom half of it for the bottom name table. It doesn't matter. If both name tables use the same tree pattern, the game still has to write dedicated tree patterns to the top half of the second pattern table if it needs trees in the top name table. Once the player crosses the threshold between 2 name tables, Commando needs to load 128 tile patterns into the associated half of the second pattern table. That is a lot of patterns to move on the fly. Let me put this into perspective. A single tile pattern is 8 pixels by 8 pixels. The 4 colors for the chosen palette can range in value from 0 to 3, seen here in binary. So each pixel requires 2 bits to represent which color selection to use. How do we pass these bits? We send all the low bits for each row via 8 bytes, and then we send all the high bits for each row via 8 bytes. So it takes 16 total bytes, or 128 bits, to define a single 8 by 8 pixel pattern. 16 bytes per tile times 128 patterns we want to replace equals 2,048 bytes that we need to push to character RAM. VBlank A just pushed 16 palette bytes, 64 attribute bytes, 32 background tiles, and all 256 sprite bytes and witnessed an invasion into the next video frames time. We can't push a byte count anywhere close to 2048 inside a single VBlank. So, Commando is set up to push 64 pattern bytes, that is 4 tile patterns per VBlank, over a period of 32 frames. It splits up the transfer to character RAM across time. We can observe this transfer with the game running. Let's slow it down and set up some graphical monitors for this. The gameplay window. Both name tables stacked one on top of the other with a gray box representing the scroll window, our current location in-game. The first pattern table for 8x16 sprites. The second pattern table for backgrounds. The second pattern table is treated as 2 halves by programming, and each half is tied to the appropriate name table like so. Once the player walks far enough upward that the threshold to the next name table is crossed, the game sends updates for the palettes, attributes, and 2 rows of the background tiles we discussed earlier, and then begins the 4 tiles per VBlank push to character RAM. As you continue to walk upward, incorrect tiles begin to scroll into view. At the same time, 4 new patterns are written to the background pattern table per VBlank, the top half in our example. Eventually, all patterns are updated. If we observe the top left corner during this walk, we can see block letters from Commando hang around for quite some time before finally being replaced. Of course, you could also cross the threshold, stop, wait for tiles to load into the pattern table, and then continue walking upward. The tiles that scroll in from the top of the screen will be correct. By the way, streaming of pattern updates isn't limited to just backgrounds. The sprites receive pattern updates on the fly as well. Later on in the first level, you encounter a prisoner that is being escorted by enemy soldiers. However, when you first stumble upon the trio, the tile patterns for their sprites haven't been loaded yet. In fact, their graphics show up really late. Here's what happens. We reach a name table threshold and lots of graphical updates are sent. The scroll window jumps. The game begins loading new background graphics to the top half of the background pattern table. The prisoner and escort spawn with outdated sprites, those of knife-wielding soldiers and helicopter parts. Their patterns haven't been updated yet because the game is still loading background patterns. Sprite patterns are updated in their pattern table once background pattern updates are complete. Now the scene is finally set. But don't take too long to free your buddy. We will eventually reach this enemy soldier next to a mortar weapon, another enemy with unique sprites and therefore unique tile patterns. His patterns replace those used for soldiers escorting the prisoner. This time the game logic plans for this, so it despawns the escorting soldiers. We are left with the prisoner escorting himself, and as far as I know, there's no longer a way to free him. He is despawned eventually, as his tile patterns need to be replaced with those used for this enemy on a motorcycle. You'll also notice that a lot of enemy soldier sprites were despawned at the same time as the prisoner. This was most likely a bit of sprite housekeeping, so there would be enough sprite slots available for the next in-game sequence. Finally, because we have to draw a line somewhere when it comes to Commando visual anomalies, you may see the entire screen glitch after taking a death. Something like this. The top half of the background is garbage, but the bottom half is okay. The reason this happens is actually quite simple. One of the PPU registers is accessed via address 2000 hex. We call it PPU control. Each bit in the byte you write to PPU control controls something. Before our glitch occurred, the value we passed to PPU control was B2 in hex. In binary, that would set the following. Enemy at the start of vertical blank is enabled. The sprite size is set to 8 by 16. That's true. 8 pixels across by 16 pixels tall. Which pattern table is used for backgrounds can be the first pattern table, 0, or the second, 1000 hex. We use the 1000 hex block or the second pattern table for background tiles, so this bit is set. Finally, the lowest 2 bits of PPU controller are used to set our base name table address. Our current value of 10 selects 2800 hex. Just a normal day at the office for a gameplay screen of Commando. Now, when the player takes a death, the game proceeds to reinitialize RAM values in order to reset the scene. It kicks this off by zeroing out PPU control. That means turning off VBlank enemy generation, setting the sprite size to 8 by 8, which is why the sprites you see inside the garbage have been cut in half, and most notably setting the background pattern table selection to 0, the first pattern table. So all the graphics pulled for the tile IDs that make up the background to this point are pulled from the wrong place. Little bits of sand that are expected to come from down here turn into numbers that come from up here. The attribute table is unchanged, and that is why the background colors are still intact. After initializing all the RAM values it wants to initialize, one of the first things it does is write the proper bit values to PPU control. This restores things back to normal. Commando sends the wrong control byte when it starts initializing values, and then sends the proper control byte after initialization is complete. So what we have here is a graphical representation of how long it takes to initialize the desired values in RAM. If all they wanted to do was turn off enemy, they could have taken the current PPU control value and ANDed it with 7F to clear the VBlank enemy enable bit, leaving sprites and background pattern controls intact. We could change the code for clearing PPU control, but it is called from multiple places, perhaps for multiple reasons. Plus, it's only a minor annoyance. But what about this mess when scrolling? We know the details concerning why it happens, but how bad is it? How can we fix it? I wrote a script that will output a list of what was just executed inside VBlank whenever it doesn't finish on time. We see when we returned from the NMI handler, indicated by the current scan line and PPU cycle, as well as how long the handler took in CPU cycles. If no overrun occurs for a given VBlank, nothing is reported in the script window. Our goal is to optimize code and eliminate overrun. I created a save state at the start of the game to use as a benchmark. If we scroll upward, we see 2 jumps occur immediately. We encountered 3 instances of overrun. The big jump when we crossed the name table, a second instance with no glitches, and a third instance with a micro jump. Let's label them. We'll call the big jump overrun A, the instance with no visible glitches overrun B, and the micro jump overrun C. We need to optimize just a little bit of code to fix these 2 minor overruns B and C, and we have a great code candidate for this. The loop that writes the next row of obstacles to RAM. While moving the execution of this code before vertical blank is the better option, we could simply optimize this existing loop to make it more efficient. That would remove the micro jump and get rid of this unnoticed overrun as well. Commando would seem to need a lot of indices for loop logic. It needs a third index for this logic to work. The processor only has 2 indices and we're fresh out. So after using Y to get the obstacle value from the ROM at the start of the loop, it converts Y to the proper index value for writing to RAM. In short, extraneous math is performed for index conversion each time through the loop, and it has to loop 16 times to write all the new obstacle data to RAM for our new pair of rows. My solution is to use a decrementing loop, which looks like this. Index X is used for the pointer to RAM for writing obstacle data. Index Y doubles as both the pointer to ROM for retrieving obstacle data as well as the loop counter. This gets rid of the unnecessary math of index conversion and therefore saves CPU cycles. As a matter of fact, it cuts obstacle looping time in half. Let's see if it removes that micro jump while scrolling. It does. The B and C overruns are no longer logged to the console because all work completes within the vertical blanking period. But here's a question from before this fix. Why did writing this second row of tiles and obstacle bytes cause a micro jump in overrun C, but writing this second row of tiles and obstacle bytes in the earlier overrun B did not? The code for loading our second row of tiles and obstacles contains 3 instances of this LDA instruction. It takes a base address and adds an index to it in order to retrieve a byte. The instruction takes 5 cycles per execution, unless a page is crossed when the index is added, in which case it takes 6 cycles. What is a page cross? A 16-bit address consists of 2 bytes. When we add our index to it, we have the address for the byte we want to load. Pretty simple. The loop continues to increase this index value so we can load the next byte and so on. But once we pass the maximum value of FF, this lower byte has to roll over. That means the high byte needs to be incremented by 1. This page cross is responsible for requiring 1 extra cycle to execute the LDA statements here. Let's compare overruns B and C from before we implemented our fix. Here is overrun C, the one with the micro jump. VBlank time was used to draw the second of 2 new rows and write the obstacle bytes to RAM, of course. We returned on scanline 0 PPU cycle 50. Here is overrun B, the one without any graphical anomalies. VBlank time was responsible for performing the same tasks, and yet we returned on scanline 0 PPU cycle 13. When we write the associated obstacles to RAM during overrun C, a page cross occurs 12 times because our added index value pushes us across a page boundary for the execution of those LDA statements. And yes, duplicate ROM addresses contribute to this total. This means 12 extra CPU cycles are required for processing versus the earlier overrun B. That really doesn't sound like much, does it? Since the PPU runs at 3 times the speed of the CPU, it took about 36 extra PPU cycles. Now there is a margin for error here for other code executed during VBlank, but the PPU cycle difference between these 2 examples would seem to check out. This is an incredibly short amount of time that makes a big difference. A single scan line is 340 PPU cycles, so 36 out of 340 PPU cycles for one scan line of one frame arriving at a rate of 60 frames per second means the difference in execution time between these two overruns is about 0.000000674 seconds. Overrun B results in no graphical glitches. Overrun C takes this much longer and results in a micro jump. While this is an isolated example, it illustrates that any VBlank instance, when we write the second row of tiles to the PPU and write obstacle bytes to RAM, may result in a micro jump if page crossing is involved. Of course, this analysis also depends on the accuracy of a given emulator. Ever see someone mention cycle accurate emulation? Well, it's needed in this example. Fortunately, our code optimization saved a lot more than 12 cycles. That should be enough breathing room for CPU time that all micro jumps have been eliminated. In fact, the longer of our two examples ends about 3 scan lines earlier now, and that puts it back inside of VBlank, which is where it should have been in the first place. Unfortunately, this didn't help our big scrolling jump of Overrun A at all, as obstacle code isn't executed during that vertical blanking period. Can we do anything to improve this monstrous 11 scan line overrun? Let's see. The palette work split into 2 subroutines that we mentioned earlier could be optimized in the following manner. The first subroutine selects the program ROM bank for palette information retrieval and then saves it to RAM using a loop. Let's eliminate that loop's execution. For the second subroutine, let it load from the ROM and write to the PPU. So we'll also eliminate the write to RAM here. Yes, you could use RAM to queue up palette bytes outside of VBlank and then transfer them to the PPU inside of VBlank for even better performance. But hey, this change is easier. Anyway, let's check that big scroll jump again. Returned on scan line 8. Not bad. And the results of this optimization are noticeable in game as well. Because we finished up work at an earlier time, the scroll window doesn't jump down as far. What else? Well, that full attribute table write really bothers me. We don't need to write the entire 64-byte attribute table during a single VBlank. We just need to write enough attribute bytes to set colors for the upcoming rows of background tiles. That's 8 bytes. In fact, let's change this loop value to 8 and only write 8 bytes. If we examine the PPU viewer and take a step after this change, we can see that we wrote our row of tiles at the bottom of the name table that we just scrolled onto the screen indicated in red. We also wrote 8 attribute bytes to define colors for the wrong location, but that is expected. We are just interested in execution time saved at this point. Which bytes we write where can be fixed later. And in this case, 8 is enough. A write of 8 attribute bytes would take care of our palette needs for a vertical distance of 4 rows of 8x8 tiles, or 32 pixels worth of vertical scrolling at a time. The NES has 240 pixels of vertical resolution, so this bottommost set of attribute bytes only needs to provide 2 rows, or 16 pixels, and that is why it appears shorter. Now, of course, only writing 4 rows of attribute bytes per loop means we'd have to write attribute bytes more often across VBlanks of multiple frames for this change to work. But small byte writes stretched across time help maintain performance better than an attribute bitsplosion inside of a single VBlank. Let's look at the big picture and talk about rearranging things for something like this. You could perhaps move the obstacle byte write outside of vertical blanking time B, as we mentioned earlier, and replace the reclaimed CPU time with 8 byte writes for the attribute table. So you wouldn't only reduce the time required to write attribute table bytes by going from 64 to 8, you would also move the attribute table update from vertical blanking time A to time B. Redistribute the workload. That would be nice, but at this moment, our setup looks like this. We write 8 attribute bytes to the wrong place here, but with the time saved from it, the jump is not nearly as jarring as it was. And we have reduced the overrun to returning from NMI on scan line 0 of the next frame. So close. This combination of reducing time required to execute tasks and changing the moment in time those tasks are performed prevents code intended for execution during a VBlank period from encroaching on the next frame's draw time. This encroachment, or invasion as I called it earlier, is what causes many of the unintended graphical glitches in Commando. And now that we have made these necessary changes, we can see the result of those changes in action. A result which would look something like this. Full disclosure, I didn't finish all the modifications, but the results are easily simulated. Commando is a fun game, and to be honest, just a little bit of tweaking under the hood could really tighten things up. Well, I hope you've enjoyed this examination of Capcom's dive into the Famicom pool. Please like and subscribe for more videos like this one. I also have a Patreon available if you're interested, and thanks for watching.